Alright, so this is our second video dealing with acids and bases, and we're going to talk a little bit more about pKa. We kind of briefly mentioned this in class. I want to give you some info on pKa, and we're going to talk more about this in class. So I just want to get you wet your whistle with pKa. Alright, so we talked about in class that most organic acids don't readily dissociate, but they have to be deprotonated. And we talked about earlier about deprotonation converting the acid into a conjugate base, and depicted here is just a little schematic of what we did. We said the acid gives up hydrogen to the base. The acid becomes takes the pair of electrons here heterolytically, becomes the conjugate base, and then the base picks up the proton heterogenically and becomes the conjugate acid. So A minus here is what we call our conjugate base. So the pKa of AH, which is this species right here, right, or the ease with which H comes off and goes with B, that's going to be determined by how stable A minus is. Okay, and so when you think about this, we talked about this being a breakup. Think about H being sympathetic to A. Okay, if H knows that A cannot handle that negative charge that's being left behind, H is not going to readily leave with B. However, if H knows that A can handle the charge, then H has no problem leaving with B because A can handle itself. Hopefully that makes some sense. All right, so let's look at pKa, and we're also going to talk about some factors that influence pKa, namely hybridization, induction, resonance, electronegativity, and then size. So we'll look at those factors. All right, so let's keep going here. This is a rule of thumb. pKa is dependent on the stability of the conjugate base. So the more stable the conjugate base is, the lower the pKa will be for a particular acid. All right, so here conjugate bases, the reason for that rule of thumb, the reason we can say that is because we know that conjugate bases want to delocalize charge. They want to, because they pick up a pair of electrons and many times become negative, they want to take that negative charge and delocalize it. Or remember, we talked about this term before, or spread it out over as many atoms as possible if it's through resonance, or put the charge on an electronegative atom, or use induction, or whatever means that conjugate base stabilizes itself through many ways. All right, and so what I have here is a little mnemonic for you to remember. HIRES, HIRES, hybridization, which is a way that conjugate bases can stabilize themselves. Induction, which means that we talked about this when we talked about polarization. Can electron density be pulled away from the charge site by an electronegative atom or a functional group that's electron withdrawn? We talked about that. Resonance, can the negative charge be stabilized by spreading it over multiple atoms? Electronegativity, so is the negative charge on an atom that's highly electronegative and therefore able to handle that charge? And then size, we talked about. We haven't talked about size, but size can play a role in contributing to how stable a conjugate base is by simply by the charge being spread out over a larger surface area, creating a less dense charge. So let's keep going. All right, let's first talk about resonance stabilization. All right, resonance, we talked about this before. You have several videos on resonance, and we've done lots of work with resonance. So let's look at resonance stabilization, and in order to understand this, we need to compare two compounds that have acidic protons and are therefore considered acids. So here's acetic acid with a pKa of 4.6, and here's ethanol with a pKa of 16, and the hydrogen that's going to be deprotonated is highlighted in red. First thing I want you to notice, look at the difference in the pKa between acetic acid and ethanol. Acetic acid is 4.6, ethanol is 16. That's a huge difference in chemistry for the pKa. A difference between pKa. That's really big. Okay, so let's think about this. Let's ask the question, or answer the question, why is that the case? Well, here's the rule for resonance. If the charge on the conjugate base can be delocalized by resonance, then the stability of the conjugate base is increased, and by the same token, the pKa is decreased. Remember, low pKa means that the acid is strong. High pKa means that the acid is weak. So let's look at what happens. Here are my arrows, right? Base to proton, and the bond between the proton and the atom is bonded to. The electrons go back there. Here's my conjugate base for acetic acid. Here's my conjugate base for ethanol. All right, and then here are the conjugate acids here. All right, so let's look at it. Why is acetic acid, the pK of acetic acid, so much lower than ethanol? Well, if we look here, right, here's the conjugate base here of acetic acid. Here's the conjugate base of ethanol. What do you notice? What can I do to the conjugate base of acetic acid that I cannot do to the conjugate base of ethanol? Right, let's look at it. I can actually do resonance and delocalize that negative charge over multiple atoms. So now the negative charge goes from this oxygen to this oxygen here, and I'm able to do resonance. And what did I say earlier? If I'm able to delocalize the charge through resonance, that means that the conjugate base is going to be more stable, right? There's no resonance for ethanol, therefore the conjugate base is not stabilized. And knowing that, that's how we can explain the difference in pKa between those two acids. So here's your second pop quiz. Can you explain why sulfuric acid has such a low pKa? And I'll give you a hint by showing you what the conjugate base is. All right, so here's the conjugate base. If one of the two protons on sulfuric acid gets deprotonated, can you explain why this has such a low pKa? Again, the pop quiz is worth 3 points. So take out a piece of paper, pause the video, and go ahead and try and work on this and see if you can explain it based on what we just learned. All right, let's talk about another method for stabilization, is induction. All right, and so we talked about the inductive effect earlier, meaning the ability of an atom to polarize a bond. It's also based on electronegativity. So here's a bond, inductive. The bond is polarized by induction because chlorine is more electronegative than carbon. This is a polar covalent bond. Remember, if the difference in electronegativity is between 0.3 and 1.4, that bond is considered polar covalent. Notice the dipole is going in the direction of chlorine, and if you look here in the bond, the two electrons, although they're shared, they're unequally shared. That's another definition we learned earlier about polar covalent bonds. So we see that there's a dipole present, meaning that there's some charge separation, and the reason is because this bond is polarized through what we call induction. All right, but induction also works if you have an electronegative atom or group of atoms proximal to a charge. If you look at this molecule here, there's a negative charge on oxygen, but there's a chlorine adjacent to that charge. And so induction works that way also, because this chlorine can still inductively pull electrons towards itself if it's proximal to the charge, right? Or that's just a fancy word for the distance to the charge. So if it's close to the charge, it's able to have some inductive influence on that charge and help to stabilize it. All right, so let's look over here and make a point that the further away the chlorine moves from the charge, right, the less the influence. So the further down the chain this chlorine moves, right, you can see it's getting further and further away from the negative charge that's here. It's getting further and further away, and as it moves further away, its influence on the charge, meaning its ability to help stabilize that charge, decreases. All right, so let's look at another example here. Right, again, we're going to look at acetic acid, which has a pKa of 4.6, and then trifluoroacetic acid, which has a pKa of negative 0.3. All right, and so when we look at these two acids and we go through the mechanism, we show the arrows going from acid plus base to conjugate acid plus conjugate base. These are my two conjugate bases. And for inductive stabilization, if we can take the charge on the conjugate base and delocalize it through induction, then that charge is going to be more stable. Now, one thing to note here is this, right? Both of these compounds, both of these conjugate bases are able to do resonance, right? So how do we account for the difference in pKa? This is 4.6 and this is negative 0.3. Very low pKa means that that is a very acidic proton, means that this is a very stable conjugate base. So how do we account for this, right? So there must be something else that's contributing to the low pKa and the stability of this conjugate base, and that something else is this trifluoromethyl group here, this CF3 group here, right? Fluorine is a highly electronegative atom, and so this CF3 functional group is just sucking electrons that or electron density this way, and it's pulling electron density away from the negative charge here. When that happens, that's called induction. It's the same concept of induction that we covered before. When that happens, what we see is the pKa of trifluoroacetic acid drop tremendously because this negative charge is now stabilized by induction. So that hydrogen has no problem leaving because what's left behind can take care of itself, if you remember the analogy I used earlier.